I did send you the solutions for chapter 4. In a little while, I should be able to send you the solutions for chapter 5 also. But I think you should definitely start working, on the problems themselves. All those problems are pretty short, easy problems that are designed to kind of help you with understanding the material better. So I hope they are useful. So let's continue with some basic group theory. Last time we introduced the concept of conjugacy classes, and that's one way of introducing an equivalence relation into a group. And so let me just review this a little bit in here. Suppose this is a group. There's a way to kind of divide this group up into disjoint sets. And you say that any two elements, G1 and G2, fall into the same equivalence class that is called a conjugacy class if G1 is related to G2 by a formula that looks like a similarity transformation. Okay? In other words, given any two elements, if there exists some element P, doesn't matter anywhere in the group. If there exists some element P that these two elements G1 and G2 are related in this fashion, then G1 and G2 are said to fall in the same conjugacy class. Yes?
The P inverse isn't what's on the left side, doesn't matter.
Doesn't really matter because this P could be regarded as the inverse of something else, okay? And this P inverse is just a group element. So one is necessarily the inverse of the other on either side. And so, and we have shown that since this is an equivalence relation, all elements in this in the same, all these different conjugacy classes must necessarily be disjoint from each other. Which means that there's no element that can fall into different conjugacy classes. Okay, so this is one way of cutting up the group into disjoint subsets. Now, there are certain special situations. The element E is a conjugacy class by itself. Okay, quite obviously, and I think that's a rather trivial case. Now, we're going to make use of this concept a little bit later. We'll come back to it. But for the time being, let me introduce another equivalence class. Two different kinds, actually. That's called left and right cosets. So let me introduce these in turn. So again, given a particular group, and a coset is mentioned with respect to a particular subgroup. So let's say you've got a group G, and let's say you've got a proper subgroup, okay, H. A proper subgroup is a subset of G, is a proper subset of G, which means it's not the same as G itself, okay? It's smaller than G itself. That is a group in its own right. As I said, this subgroup must contain the identity element of the entire group, as well as many other things, so that this thing is a subgroup, and it's a subset, obviously, of G. Now, the two trivial subgroups, one is the identity element E itself, and the other one, of course, is the entire group. Okay? So let's say that we have one such subgroup, and I can use this subgroup to again cut up the entire group into different pieces, if you will, okay, disjoint pieces, with H itself being one of the pieces. And now how do I define each piece other than H itself? There are a couple of ways to do that. Let me talk about the so-called left cosets first. We say that any two elements, G1 and G2, any two elements are said to belong to the same coset, left coset, if, with respect to H, if G1 inverse times G2 belongs to the subgroup H. Any two elements are said to belong to the same left coset with respect to H if G1 inverse times G2 is an element in H. Now, obviously, this is well, I don't know if it's too obvious, but it's not too hard to show that this is an equivalence relationship. Okay, so if G1 is related to G2 in this manner, then you can see that G2 is related to G1 in this manner also, right? Why? Because if you write G1, G2, the inverse of that, okay? If this thing is in H and H is a subgroup, then the inverse of this must be in H also, okay? Because H is a subgroup. But the inverse of this is G2 inverse G1, okay? The inverse of AB is equal to B inverse A inverse, and you can show that pretty easily, okay? So if G1 is related to G2 in this manner, then G2 is related to G1 in this manner also, and then you can see that this is an equivalence relationship. Obviously, anything in H is related in this manner, okay? Because you take any element in H, H1, H2, H1 inverse times H2, because H is a subgroup, must necessarily belong to H also, okay? So any two elements inside of, all elements of H form a particular left coset. All other cosets can be broken down in this manner. Any two elements are said to belong to the same coset if those two elements satisfy this condition. Now, this is one way of specifying a subgroup, okay? There's another way of specifying the subgroup also, the coset rather, also, and that is you can write a particular coset as some G inside of, some little g inside of G multiplied by H, and by this I mean all the elements G, H, such that H is an element of H. Do you understand what that means? Okay. You pick anything out of G itself, okay? And then you multiply on the left, on the right. Well, G stands on the left. That's why this is called a left coset. You take all the elements of H, any element in big H, and multiply it on the left by the same G, and then you get a certain set, okay? So this set consists of elements such as GH1, GH2, all the elements that you can form in this way, where you run through the entire subgroup with all its elements. And this forms a set. You can show that this is the same as this guy in here, okay? That is characterized by a particular G inside of this coset. The reason is this: you can multiply by G1 on the left. So here you have G2 must be in G1H, right? See how that is obtained? Multiplying by G1 on the left. So G1 times G1 inverse gives identity, so this on the left side, you're just left with G2. And on the right-hand side, you multiply by G1 on the right-hand side, you multiply by G1 on the left, okay? So therefore, you get something like this. What H is, this letter means the whole group, and so this set means you take this particular G1 and multiply through by all elements inside H. As I said, this is an equivalence relationship, so therefore, all the different left cosets must be disjoint. That means that no one single element can belong to two different cosets. Okay? All of those cosets are disjoint. And I think the the most usual way probably is writing the coset in this particular way. This is called left coset. I would call it like this, the left coset characterized by G. The whole coset is characterized by just this single element G, okay? And the whole coset consists of all the elements when you multiply that one G on the right-hand side by all the elements of the subgroup H, okay? So all the elements look like this, right? There's, you put in all the possible elements, little h of big H, and you get a certain set with the same G. And this set is called the coset that is characterized by G. And obviously, if it's the whole coset consisting of different elements is characterized by just the one group element of G. And so therefore, you can sometimes also designate, now I'm not going to do that first, but it makes sense to, I'm going to explain that notation a little bit more carefully later on. But it makes sense to just write the whole coset in terms of a single representative like that, okay? You see two different elements. If they belong to the same coset, then the coset is characterized by any one of them, okay? And so it doesn't matter which one you use as the representative, okay? Now this is called a left coset, the set of left cosets. Let's say left cosets, each one of which is characterized by GH, okay? Now you can have right cosets also. Similarly, you can introduce the notion of right cosets. A slightly different way of breaking up the group into different disjoint sets. This time, you break it up, but the breakup is different in general. It won't be the same disjoint subsets as the set of left cosets. In general, the set of right cosets is different from the set of left cosets. And you say that any two elements, G1, G2, are said to belong to the same right coset if G1 times G2 inverse is an element in the subgroup H, okay? And similarly, you can characterize a particular right coset by this symbol in here, okay? Where you use some G within the original group big G, and you multiply G on the left-hand side by all elements of H. Then the set that you get is said to be the right coset that's characterized by this particular group element. So when you write it in the set notation, this consists of all the elements Hg such that H in H, like so, for some G in G. Similarly here, for some G in G, okay? Now, I have to admit that this is a little bit abstract at this point, okay? But as it turns out, this will be a very useful way of, a useful couple of ways of breaking, of introducing equivalence relationships. The first one, again, is a conjugacy class that we explained last time. This one is called the left cosets, and this one is called a set of right cosets. In general, the left cosets are different from the right cosets, which means that, in general, GH is not the same as HG, okay? A left coset characterized by a particular group element little g is not, with respect to the subgroup H, is in general different from the coset characterized, or the right coset characterized by the same G. Yes?
Is H any subgroup within?
H is any subgroup. H is any subgroup. It can be the entire group itself, in which case it would be trivial. It can also be the identity element by itself, which is also trivial. Okay? So in general, we're talking about some proper subgroup of H, which is neither the identity nor the entire group. It's a thing that's bigger than the identity, but smaller than the whole group, okay? And so you can, with any subgroup, you can form the set of left cosets according to this manner, or you can form the set of right cosets according to this manner. The set of left cosets is in general not the same as the set of right cosets, which means that this is in general not the same as that, okay? So with respect to the same subgroup, the entire group can be broken in two different ways, okay? One called the left cosets and the other one called right cosets. And of course, in each case, all these sets are disjoint. That means the intersection of any one of those sets is exactly the null set, okay? Okay, now, so having introduced, I need to I made some statements, but I better justify those statements, I guess. The two partitions are not the same. I've mentioned that already. And the designation, these two names, left coset and right coset, is based in this manner of writing it. Left coset means the G occurs to the left of the subgroup, and right coset means that you write it in this way, the G occurs on the right of the subgroup. You have to distinguish between the two because group multiplication is not necessarily commutative, okay? And okay, let me justify a couple of things. Let me show that explicitly that the left cosets, for example, can be written like that, okay? So, as I said, the left coset consists of all elements of this form, okay, where H is any element, little h is any element in the subgroup big H. So let's just pick two elements in the subgroup big H, and let's just write for one and the same G, write these two elements, GH1 and GH2. As this way of writing the coset implies, these two must be two elements in the same left coset, okay? In other words, that left coset that's characterized by this G in here. Now, I have to prove, what I want to do is to prove according to this definition that these two things belong to the same left coset, okay? So let's say this is a first element, and this is a second element in the original group. And I want to prove that these two elements are related to each other in this fashion in here. If I can do that, then I have proved that these two elements are elements in the same left coset, okay? So indeed, let me do this, GH1 inverse times GH2. And clearly, this is H1 inverse, G inverse, GH2. Is that okay? You take the inverse of GH1, it gets you H1 inverse times G inverse. Quite obvious. But these two, the product obviously gives you the identity, and therefore this is actually H1 inverse multiplied by H2. But both H1 and H2 are elements in the subgroup H, and so therefore by the rules of group multiplication, this one is also in the subgroup H. And so therefore, I proved that if you start off with this definition of the left coset, you get back this definition of the left coset, and you can go the other way also, and thereby we have justified that these two are exactly equivalent ways of writing, defining a particular left coset. And in an entirely similar manner, you can also do it for the right cosets. And I'm going to leave it up to you to do that, okay? All right. As I said, obviously, this guy itself is a left coset, right? H is itself is a left coset because H is the same as this guy, where E is the identity. E multiplied by anything inside of H gives you something in H. So therefore, this is quite trivially obvious, okay? And so that means H itself is its own left coset, a sort of a special one. And there are a bunch of others also. Okay? Yeah?
Does the identity within H have to be the same as the identity of G?
Yeah. Yes, because that's the definition of a subgroup. A subgroup, let's say you're given a group, so there's this identity element in here. And if there's a subset called big H, which includes this identity, that is the original identity, and if this subset is a group in its own right, then this thing is called a subgroup, okay? So obviously, there can only be one identity when you talk about subgroups. That is the identity of the original group, okay? All right, so we got through the, and the thing to remember is that in general, the set of left cosets is different from the set of right cosets, although there's one element which is the same in each case, and that is H itself. But all the other bundles are different, so to speak. Okay? So as I said, corresponding to a particular G, GH is in general not equal to HG. Okay? So the left coset corresponding or represented or characterized by this G is in general different from the right coset that is characterized by the same G. Okay? Simply because group multiplication is not commutative. Okay? However, if you have this special situation for any G in the original group, big G, if this is so for any little g in big G, then the subgroup H is called a normal subgroup of G. Important concept. Sometimes it's also called an invariant subgroup. Normal subgroup or invariant subgroup of G. Okay, why is it called an invariant subgroup? Because you can multiply this equation on the left by G inverse, and then you will get this. Okay, and that is you transform, consider H as some group element. Consider, you take any element inside a big H, right? And you think of performing this sort of like a similarity transformation with respect to any G. You get back H itself. So in this sense, we say that H is invariant under any similarity transformation given by any element in G. So that's why it's called an invariant. Okay? After a similarity transformation, it gives you the same thing. Obviously, if you have the general situation like this, then H is not equal to G inverse H, G. So that H then is not an invariant subgroup. It's just some subgroup, okay? So out of the possible subgroups of a particular group, there are these important ones called normal subgroups or invariant subgroups. And these are the ones which make possible the notion of a quotient group. Okay, so let me tell you how a quotient group is formed.
You know why it's conormal?
It is so normal. The other part is, the other way it's called abnormal. I don't know the answer to your question. Yeah.
Perhaps because that looks like a similarity transformation which involves orthogonal matrices, and normal is another word for orthogonal.
Well, the point is, we are talking about things groups that are much, much more general than orthogonal groups. Okay, but you can think of it in many ways, I suppose. But perhaps the term invariant carries a little bit more meaning in that sense in here. Okay, so H remains invariant under similarity transformation given by any G. Okay, and this will become very, very important in quantum mechanics also. You use group theory in quantum mechanics when you talk about invariance of the Hamiltonian with respect to all kinds of transformations and so on and so forth. Okay. Okay, so let's say we have a normal subgroup. Are we going to make use of this normal subgroup to partition the group? Well, it's obvious. If the subgroup is normal, GH is equal to HG, then the left and right cosets are exactly the same, right? So based on one particular normal subgroup, there's only one way using this kind of equivalence relationship to partition the original group. One way. Because then the left cosets are the same as the right cosets. Okay? And so then, there is the possibility then of treating each of these cosets as a particular element of the quotient group. Okay? It's just like grouping a whole bunch of things in the original group and make it as one. Okay? Since these sets are disjoint, you can always do that. Okay? It would not work if these things were not disjoint. Okay? So then you can form each of these as the element of a particular group, and that is the group that we call G divided by H, okay, or the quotient group of G divided by H. And now, you can't just say that. You can't just say that these things form a group. You have to introduce a certain multiplication rule between this thing and this thing, for example, so that the multiplication rule follows the general definition of multiplication for any group whatsoever. So you have to prove that it's closed. You have to prove that it's associative. You have to prove that there exists an inverse. And then you have to prove that there's an identity and so on and so forth. Okay, so so let me now introduce the multiplication in this way. Now remember, in this case, since the left and right cosets are the same, so a particular G inside of the original group serves to characterize a particular coset, right? So this whole thing this whole thing consists of many elements, right? That are related in a certain fashion. But each one of them belongs to the same coset, and I can take each one of these to characterize the same coset. Okay? So in other words, a particular coset is characterized by just this little g in here. And so I'm going to write the coset that's characterized by this g using this symbol. I'll say why this is useful. It's a funny symbol which may not be too familiar, but this is good enough for our purposes. So this does not mean one particular group element inside of big G. This means the whole coset characterized or represented by this little g. That's why the little g, of course, I can have two different g's characterizing the same coset, right? Because I have many different group elements in the same coset. But one of them is sufficient to characterize a whole coset. Okay? So let's say that this characterizes a whole coset. And supposing I have another coset. Now let me say one of them, one coset is characterized by G1, and another coset is characterized by G2, okay? So this is a whole coset, this is a whole coset. So now let me just define a multiplication such that this coset multiplied by this coset gives me another coset. Which one? This is a multiplication rule. Do you see how it works? Okay. So let's say there's G1 here, there's G2 here. Let's say we take the case of where G1 and G2 belong to two different cosets, but G1 serves to represent the whole coset here, and G2 serves to represent the whole coset here. So here I have a multiplication rule which tells you how to multiply this coset by this coset. Okay? Which one do you get? You get the one that's characterized by this group element. Now G1 times G2 may be elsewhere. Let's say G1, G2 as a product of these two things sits over there. Okay? So here would be the case where this coset multiplied by this coset gives you that coset. All right? Now, if G1 and G2 sits inside the same coset, then that's quite obvious, right? If G1 and G2 sits inside the same coset, what happens? Well, actually, still you have to be careful. Now, G1 and G2 may still sit here, okay? G1 times G2 may still sit here, okay? But here, if G1 and G2 sits inside the same coset, it just says that this coset multiplied by itself gives you this one, that's all. Okay? So whatever G1 and G2 are, this definition always works. Okay? Whatever G1 and G2 are, this definition always works. Now let me take G1, let me take a special case. G1, let me write down the definition first. G1 times G2 defined to be G1, G2 bracket like that. Let me take two elements within H1 and H2 within the normal subgroup itself. Okay? Because this is a subgroup, let's see what I get by H1, H2 like that. Now, of course, this, you see, this is H and this is H, right? Because they both sit inside the normal subgroup. Now, according to this definition, this equals what? Bracket of H1, H2. So where does H1, H2 sit? Inside a big H. So therefore, this is also big H. So therefore, you have big H multiplied by big H gives you big H. So this already gives you a hint that this is the identity. That this is, big H itself is the identity element in the quotient group. Yeah?
So the quotient group is a sigma group?
No, never said that. Quotient group is the group whose elements are these cosets. And this equation gives you the multiplication rule, so to speak, for the set of things whose elements, set of elements, each one of which is a coset like this. So you're multiplying a coset by a coset. This rule tells you how to multiply a coset by a coset. Okay? Now, let me take another situation where I have G multiplied by some H, let's say. Okay? Now, obviously, this is just H, right? So little h is some element inside. So the coset that is represented by this particular element in big H would be big H itself. Is that okay? And so, well, by the multiplication rule, what do you get? This is GH. right? But where does GH sit? Which coset? Same coset represented by this one, right? Because any coset represented by this one, the elements are always G multiplied by some element in H, okay? So this is H, okay? Similarly, H times G is equal to HG. Now this time it's a right coset, but the right coset are the same as left cosets if this is a normal subgroup, so therefore this is just H also, okay? So this is H. So H multiplied by G is also H. So it tells you that the entire big H itself is the identity element in the quotient group. Okay, so that's why this definition makes sense. It's a little abstract, right? Is it hard to swallow?
So
Yeah.
basically, the identity, that basically means that in that case, G is equal to G and H is,
I'm sorry, which equation are you talking about?
since we've proven that G and G H is equal to,
Yeah, since I proved that, I have proven here that G, which is one coset, multiplied by this is a coset in itself, is equal to H, okay? So this basically tells me that this coset is the wait a second. No. This just says that that H is the identity in here. Because G multiplied by the identity, oops. No, this is, sorry, I made a mistake. This is the one, this is the same as G. This is the same as little g. Okay, sorry about that. This one is G also. So H is the identity. Big H is the identity because it multiplied by anything else gives that same anything else, either on the right or on the left. So that makes big H the identity, okay? Again, I find the easiest way to kind of visualize this is to form a mental picture like this. The original set is broken up into these chunks in here. The chunks are disjoint, and all of them make up the entire group. And each of the chunks themselves can be regarded as an element of a new group that we call the quotient group, okay? It's like G being broken up by H in this way in here. And so now the final step, of course, to prove that this is indeed a group is to prove the multiplication, that the multiplication rule introduced in this manner satisfies the rules of group multiplication in general. Now, I haven't done so yet, so I've just given you a couple of examples to convince you that this is reasonable. Let me do this a little bit more formally at this point. So, we have to check that multiplication makes sense by verifying that it is independent of the representative. Okay, so we have characterized by a particular coset by this particular group element, but you have the option of characterizing it by some other element that is within the same coset. Okay, so if two elements set within the same coset, then even though they're not equal to each other, then the coset that they represent is the same one. Okay? So, so let's just take, supposing I have, suppose I take G1 and G1 prime, and both of them sit within the same coset. So let's say I have this situation, okay? G1 and G1 prime, both of them sit within the same coset. Let's say this one, G1 and G1 prime. And actually, and let's say just for clarity, let me say that G2 and G2 prime are another pair of elements which sit inside of another coset. Okay, so I also have G2 prime bracket is equal to G2. Let's say I have this situation in here. Okay. Now, if G1 prime and G1 sit within the same coset, by definition, I have G1 prime must be equal to G1 multiplied by some H1, which is inside the normal subgroup, okay? And by definition, I have G2 prime must be related to G2 in this fashion, where H2 is some other element in the same normal subgroup, okay? This means this, okay? If you have this for some element H2 within the normal subgroup, then you say that G2 prime sits in the same coset as G2, which means these two different group elements characterize the same coset. Okay? Similarly for that over there. Now, what I would like to show you is that the way to represent a coset does not depend on the representative. In other words, you can choose either G1 or G1 prime to represent that coset, or you can choose G2 or G2 prime to represent this coset. In other words, what I would like to show you is that G1 prime times G2 prime, written in this manner. I'm going to show you that this is in fact true, but for the time being, let me write a question mark. This is equal to G1 times G2. Do you see why we need to do that? Okay. That is to try to show that, again, the coset does not depend on the representative, so to speak. Okay? So let me start from this side in here, and I'm going to end up on this side. Okay? So making use of these two relationships, right? But first, let me make use of the definition for the quotient group multiplication first. Okay? By this particular multiplication rule, this must be equal to G1, the bracket of G1 prime, G2 prime, like that. Okay? By this rule in here. And now I'm going to use these two equations for the group elements inside. Okay? And so G1 prime is equal to G1 H1, and G2 prime is equal to G2 H2. Okay? Now, I'm going to make use of the special property of a normal subgroup now. If it's a normal subgroup, GH is equal to HG. That means G multiplied by some element of H must be equal to some other element of H multiplied by G. Okay? So in other words, here, I have H, some element in H multiplied by G2 must be equal to G2 multiplied by yet another element of H, like that, because of this invariance requirement. Here we have to make use of the invariance property of the subgroup. Is that okay? And so this becomes, for some, so this is equal to, so let me just write out first, G1, G2, I'm sorry, G1, G2, H multiplied by H2, like that, for some H in big H, okay? Now, this is obviously some element in H, because H is a subgroup, okay? So this coset must then be characterized by this group element, okay? Do you agree with that? Okay. Finally, by the definition again, this must be equal to bracket G1 multiplied by bracket G2 again, so I end up with the right-hand side. So I have proved this equality. What that tells us is that this multiplication rule makes sense because the letter here that characterizes the particular coset does not have to be a unique group element. As long as there's some group elements, G1 or G1 prime, that sits inside of the same coset, that would suffice. So you can characterize or you can represent a particular coset in many different ways. as many ways as there are elements in the coset, for example. Okay? Is that all right? So, this shows that the group multiplication, this group multiplication was well defined. You know, in mathematics, when you define something, the first thing you want to do is to show that it's well defined. Otherwise, it doesn't make any sense. If there are holes, there are contradictions in your definition, then it won't work. Okay. Then next, I want to show that, which I've kind of done already, that the coset that's characterized by some element inside a big H is in fact the identity. And so here we go again. So if you take, this guy is obviously the big H in here. And if you take that to multiply with any element or any other coset which is characterized by some group element in here, by the group multiplication rule, you get Hg. Okay? But by invariance, again, Hg itself must be equal to Gh prime for some other, in general, for some other group element inside of H, right? So H, some element in H times G is equal to the same element in G multiplied by some other element in H, okay? So this is what that says. And by group multiplication, I can break this down into G, H prime, okay? But H prime, of course, is just H, because H prime sits inside of big H also. And that must be equal to GH. And I think we have shown before that this is just because this H is the identity, right? That is just equal to G. No, I haven't assumed that this is the identity. I just, you know, this is, this thing is H itself. So this is of the form of the coset, which is characterized by this G in here, okay? So this is just equal to G. And so I have proved that this multiplied by G gives G itself, so this guy is the identity, okay? And similarly, it goes on the other side also, okay? Now, next exercise is that you have to prove that the multiplication defined by that is an associative multiplication. That is very, very easy. I'm going to leave that to you as an exercise, okay? And then what do you have to show? You have to show that there exists an inverse, right? You have to show that there exists an inverse. So let's show that. So I'm going to make the claim that, let's say we are given this particular coset, and I want to find what as a group element, what the inverse of that is. And my claim is this, that this is equal to the coset that is characterized by the inverse of G. That seems quite obvious, but it's a little bit of proving, okay? So here we go. What we want to show is that according to this definition, G times G inverse is equal to, after a number of steps, is equal to this, because we have shown that this is the identity. Okay? So let's start off from here first. Now, we're going to show that making use of this definition, this is true. All right? So this then is equal to this multiplied by G inverse, making use of this definition of the inverse. Okay? We don't know whether or not that is the inverse. We're going to show that. Okay? All we know is that you have introduced this symbol in here, which is defined to be this thing in here. We're going to show that this is in fact the inverse of G. Right. So according to the group multiplication rule, this is equal to that. And now, because GG inverse is the same as, well, you know that this is equal to E, okay? But let's not use that yet. You also know that GG inverse is the same as G inverse G. Okay? Which, by the group multiplication rule, is equal to G inverse bracket times G. But you know that this is equal to the coset that's characterized by this, okay? But the coset that's characterized by the identity element is which coset? Is H. In other words, it's this one in here, okay? It's the identity, okay? So we have proven that, okay? That as the inverse that is introduced in this manner is in fact the inverse of this coset in here, because it multiplied by, these two multiplied together gives you the identity. Okay? It seems to be a little bit kind of splitting hairs at this point, but I hope that you realize the chain of reasoning that one has to go through in order to establish this, okay? Now, before we move on to the next important thing, let me mention the special case of an abelian group. For an abelian group, of course, the multiplication is commutative. And for that reason, you kind of look at it as an ordinary, you use the symbol, the ordinary addition symbol, to represent the group multiplication, okay? Because A plus B is always the same as B plus A. And the inverse of a group element G is represented by minus G, so that A minus G is equal to 0. So the 0 is the identity, so to speak, okay? And so that if you're talking about an abelian group, then G1 and G2 are in the same coset if for an abelian group, there's no distinction between left and right cosets, right? Because it's abelian anyway, okay? And so that you say that G1 and G2 are in the same coset if G1 minus G2 is inside of the normal subgroup. The notation is a little bit different, but sometimes when you see it for the first time, it tends to be confusing because the multiplication symbol all of a sudden becomes the addition symbol. The thing is that in mathematics, the addition symbol is often used as, at least within the group context, as the multiplication symbol for an abelian group. Okay, simply because in ordinary addition, the process is commutative. Okay, it's just a special remark. All right. Now let us break up at this point for 5 minutes. But before we do that, let me see if there are any questions concerning what we have gone through so far. Yeah.
How did you make the leap from that portion to the identity?
Which portion? Here?
Yeah.
How do I make the leap?
Yeah.
Because this is equal to this. Because I'm suddenly using this equal. Because G times G inverse is E, so this becomes bracket E.
Okay.
And is an equality all the way
So
through.
then you were just essentially just like manipulating it to like different expressions?
Yeah, I am manipulating it into. I'm just basically showing you that that for any group element, that group element multiplied by its inverse is the same thing as the inverse multiplied by the group element which produces the identity. Okay? A multiplication by its inverse can happen both ways, so I have to show that. Okay? So G times G inverse is necessarily equal to G inverse times G. both of which are equal to the identity. Okay? All right, let's rest for a few minutes. The group homomorphism theorem, which is a very neat theorem. This is theorem 6.2 in the book, also known as the group homomorphism theorem. Which basically says this. Let F be a group homomorphism from the group G to the group G prime, and K is the kernel of F, which means all the group elements in G such that F of G is the identity E prime in G prime. Okay, let me draw you a picture. So you have a group G, you have a group G prime. These are different groups, so the identities are different things. Okay, so the identity in G we call E, and the identity in G prime we call E prime. And so now group homomorphism is not necessarily a one-to-one mapping. All that it is required to do is that F of G1, G2, where G1, G2 are separate elements in G, is the same as FG1 times FG2. Okay? So let's say G1 gets mapped by the homomorphism to F of G1, and G2 gets mapped by the homomorphism to FG2. And let's say G1, G2 is some other element in G. Then for F to be a homomorphism, this will get mapped to this thing in here, which is called FG1, G2, right? A homomorphism means that in this group, this multiplied by that gives you that. That's a homomorphism. A mapping which does not satisfy that condition is not a homomorphism. And you see clearly, we require this because we want to preserve the multiplication structure, so to speak. Okay? That's why this is called a multiplication preserving mapping. That's another way of saying it. A multiplication preserving mapping is called a group homomorphism. And so let's define the kernel, right? The kernel will necessarily include the identity, but it may be much bigger than the identity, because for group homomorphism always maps one identity to the other identity, okay? But if you have a situation where everything in this set in here gets mapped to this one single element, I hope I'm not making the diagram too confusing, right? It's like a mapping. All of that set gets mapped to the one single identity in the other group, then that K is called a kernel of the homomorphism F. Okay? It's called a kernel. It's like a little nut in there. That nut gets mapped to, the entire nut gets mapped to a single point, which is the identity. Okay? Think of the kernel as a little seed that you're biting, something like that. Okay. Okay. And now, let's also define the image of the homomorphism, which is the image of the homomorphism. Now, the idea is that since the group homomorphism need not be one-to-one, you may take everything in G, but that doesn't get mapped to everything in G prime. Okay? So let me draw you another picture so as not to confuse the first picture. Let's say that this is G, that this is G prime. let's say if all of the original group gets mapped to some subset of the other group by this mapping, then of course this thing is called the image of the homomorphism. Okay, that thing is called the image of the homomorphism. So I'm going to write it like this. That consists of all the elements G prime in big G prime such that there exists G in G such that Fg is equal to G prime. So it's clear that, that's write the condition of set theory notation like this. Okay? That's called the image. But I hope you understand kind of intuitively what that means. So you have G, you have G prime, you have K, you have I. So you have those four things now. Okay? The theorem states two things, two very simple results. Number one, kernel K is always a normal subgroup of G. Number two, when you take since it's a normal subgroup, you can form a group quotient group, G divided by K, as we discussed just now, that this thing is isomorphic to the image. Now, what does isomorphism mean? I think it should be very clear to you. It's a mapping which meets two conditions. First of all, it has to be a one-to-one, and then it has to be on-to. So one-to-one is sometimes also known as an injective map, and an on-to map is also known as a surjective map. Okay, now one-to-one is fairly clear, right? Different things always get mapped to different things. That's one-to-one, okay? On-to means that you have two sets in here. The image is the entire thing. That's on-to. So if I have a situation like this, obviously that's not on-to, because there are things here which was not mapped from the original group. Okay? So isomorphism means a one-one and onto map, sometimes also called a bijective map, being injective and surjective. Okay? Just some mathematical terminology, basic mathematical terminology. Okay, so how do we go about proving that? We have to prove a number of things. First, we have to prove K is a normal subgroup. Prove the first part. Let A and B be two elements in the kernel. Well, first of all, let's prove it's a subgroup. What that means is that if A and B are in the kernel, that A times B must also be in the kernel. Okay? So let's see what F of A times B is. Because this is a homomorphism, that must be equal to Fa times Fb. Okay? And because A and B are both inside of the kernel, Fa must be equal to E prime, the identity in the other group, and so must Fb be also equal to E prime, since both of them are inside the kernel. And so if E prime times E prime, which of course is E prime. Okay? So this says exactly that if A and B are separately inside the kernel, then A times B must also be in the kernel. Okay? So this proves the so-called closure of the group. And now, so next, let's say that supposing I take a general element G in big G, then I can write F of G. G I can always write as GE, okay? And so this is by homomorphism property, F of G times F of E, okay? And so this means what? This means that F of E must be E prime, okay? That means because anything is equal to anything times this thing must be equal to the identity. So but this thing is Fe, so Fe must be equal to E prime. Okay. What does this show? This shows that E necessarily is inside the kernel because it maps to the identity in the other map, in the other group. Okay. Now we also have to show that if A is in the kernel, A minus 1 had better also be in the kernel, otherwise the kernel wouldn't even be a subgroup. Okay. So how do we show that? We just have to show that f of A minus 1 must be equal to E prime, but f of A minus 1, and we have shown this already, is equal to the inverse of f of A, if f is a homomorphism. Okay? But since A is in the kernel, f of A must be what? E prime, right? So this must be E prime, the inverse of E prime, which is, of course, is E prime itself. So this shows that if A is in the kernel, the inverse is also in the kernel. Okay, so this is another group property, right? Finally, well, I think that's enough to prove that the kernel is in fact a subgroup. Now we have to show that it is a normal subgroup. Okay? Now, so how do we show that it's a normal subgroup? We have to show that it's a normal subgroup. So let us look at this group. Let's look at this set of objects. Take some G in here, take the entire kernel, and G minus 1 like that. So there are as many for a particular G, okay? So there are as many elements here as there are elements in the kernel, in the group K, in the subgroup K. And so let's take a particular element in here. Let's call that particular element G little k G inverse, where little k obviously is considered to be an element in big K. Okay? And now we try to map this element by the homomorphism. And by the homomorphism property, this is obviously equal to Fg, Fk, Fg inverse. Because k is in the kernel, Fk is equal to what? E prime. E prime, right? It gets mapped to the identity. Because this is the identity, this is just equal to, you can kind of take it out, okay, so to speak. It's equal to that. Okay? But we saw big group homomorphism, this must be equal to the inverse of Fg. Okay? So you have some group element in G prime multiplied by its inverse, this must be equal to E prime. Okay? And so this says what? This says that this must be in the kernel also. This must be in the kernel also. Okay? So in other words, this is equal to K. Okay? So we have proved the normal property, right? Because GK is equal to KG. Yeah?
Not J, but G doesn't necessarily have to be within the kernel.
No.
Okay.
G is any element.
Okay.
Okay?
G, K, G inverse.
K is the kernel. G times K times G minus 1 is in the kernel if K is in the kernel for any G. Okay? So we have proved that this is a normal subgroup. I guess conversely, well, no. So wait, we have to be careful. I'm jumping the gun in here a little bit. I'm jumping the gun in here a little bit. So far, I'm saying that this element must be in the kernel, right? So far, I have only proven that GK, G inverse, since any element in here must be an element in K, so far I have only proven that it's a subset. I haven't quite proved equality yet, I guess. So in order to prove equality, I have to prove the other way, right? So I have to prove that K must also be a subset of G, K, G inverse. If I can do that, I can prove the subset relationship both ways. That means the two sets are in fact identical sets, are equal to each other. Okay? All right, this is also quite simple. So I have to prove that if something is in K, it must also be in this guy in here. Okay? For some G. And so it goes like this. Let's take some K, little k in big K. Little k is inside the kernel. I am going to write K in this way. K is equal to G inverse K G inverse, obviously. Okay. But that's obviously in K. That's the first part. Okay? That's obviously inside of K. I can write this as K prime. Okay? By the first part, the GK inverse is in K. So this element must be something in K, so I'm going to call it K prime. Okay? And so there exists a K prime where K is written as G K prime. There exists a G where K can be written as G K prime G inverse. In other words, I have proven the second subset relationship. So I have proven it both ways. If A is a subset of B and at the same time B is a subset of A, then by basic set theory, A must be equal to B. Okay? So that in fact I have proved that G, K, G inverse and K for some G are the same sets. Okay? And so that says that K is a normal subgroup. We have proven K is a subgroup, and now we have proven that it's also a normal subgroup. Okay? So that proves one, K is a normal subgroup of G. K being a normal subgroup of G, then it makes sense to make this quotient subgroup, okay? Where you divide G up by means of K into separate cosets. So let's say this is G and this is K. That is the kernel. And so now you can use this K, which is a normal subgroup, to break G up into the different cosets. Okay? Where again, each coset is just characterized by some group element. And my task is now to show that it is isomorphic, the subgroup is isomorphic to the image of the original homomorphism. Okay? So the picture is like this, right? So this is G, this is G prime. The image is this subset of G prime, which is mapped to from elements in K. So all of K just gets mapped to the image, okay? No, the image. Sorry. Not all of K. All of K just, yeah, you're right. All of G. All of K just maps to the identity. All of G gets mapped to this image in here. All of G. Thank you. Okay, the second part, which is really the more important part, what it says is that there's a one-to-one and onto relationship between the cosets here and the elements in here. Okay? So one of these would correspond to one element in here, 1 to 1. And then this would correspond to the identity element. Yeah?
So basically speaking, even though G isn't onto G prime, it is onto the image.
The quotient group is onto the image.
Okay.
The quotient group, not G itself. G is obviously not onto, right? Because there are whole portions of G prime which is not obtained from G, okay? But the quotient group is. Each coset in here, there's a mapping, a one-to-one and onto mapping which maps some coset here to some element in the image, okay? So that basically provides you with a neat way to study the image of a particular group homomorphism. It is structurally the same as the quotient group of G divided by its kernel. Okay? Now let's try to prove that. Yeah, okay? So let's find that mapping which does the job for us, so that there's a 1-1 relationship from that mapping between the quotient group and the image. And so let me call this mapping F. It's supposed to take you from G over K to the image. And the map is defined like this. Now, I take some element inside of the quotient group. Some element of the quotient group is always representable by something like this, by one representative, okay? And here's the definition, right? Definition says that this particular coset gets mapped by G to what? To F of G. F of G must be an I because F was the original group homomorphism, right? So this takes you from something in the set of cosets to something inside the image set. Okay? So this is a definition of the mapping, and I'm supposed to show that this mapping is in fact 1-1 and onto. If I can show that, then I have shown this relationship. Okay? So let's say that I take some coset, and I'm going to write this coset as the set G multiplied by K, right? By the definition, which is the set of all G little k when K little k is in big K. Set theory notation. Now, okay. Let's see. What happens now if I do first of all, I'm going to show that this is a group homomorphism first. I'm going to show that this is a group homomorphism, okay? So I want to show this by writing something like this. How much time do I have? Can I take that picture away? See that picture? That's okay. No, I want to leave the theorem here. So let me take phi and use it to map the product of these two group elements in the quotient group. Okay. By the group multiplication within the quotient group, this is equal to phi mapping this, right? Using the basic definition for group multiplication within the quotient group. this quotient, this thing in the quotient group multiplied by this thing in the quotient group gives me this other thing in the quotient group, okay? And now I make use of what? The definition of phi in here. And so I'm going to end up with f of G1, G2. Now f is a group homomorphism, right? Which is a basic assumption. And so therefore this becomes FG1, FG2. And I make use of the basic, I make use of this, okay? F of G1, F of G2 becomes phi of G1 multiplied by phi of G2. Is that okay? By that definition of phi. Okay. So what I have shown is the group homomorphism property, right? Do you recognize that? So phi is a group homomorphism. So therefore, phi is a group homomorphism. It's a homomorphism because G over K is a group. And, I have to show that I is a group. I is a group also. And that's quite obvious. I is a group also. Okay. So why is I a group? I is in fact a subgroup of G prime. I as a subset of G prime is a subgroup of G prime. I is the image which sits, of course, inside of G prime, and we have to show that it is a, other than being a subset, it's a subgroup. Do you know why? So if I is a subgroup, let's see. So I have to prove that if G1 and G2 are both in I, then G1 times G2 is also in I, okay? That proves the, and then I have to show that the image is, if some G is in I, then that the inverse is also in I. And of course the identity is in I. That's a given. So really, the only thing to prove is this. So if G1 and G2 are both in I, that means, let me write this. Let me write the primes for these guys in here because they are in the group G prime, okay? So if G1 and G2 are both in I, then the G1 prime there must exist some G1 in G such that f of G1 is equal to G1 prime, okay? And similarly, there must exist some G2 in G such that f of G2 is G2 prime, okay? That basically says that G1 prime and G2 prime are both in the image, okay? Now, then, if I would like to see that G1 prime and G2 prime is also in I, so, but G1 prime times G2 prime is equal to f of G1 times f of G2. But because f is a homomorphism, it's equal to f of G1, G2. But G1, G2 must be in G also. So for G1 prime times G2 prime, there exists some G such that homomorphism takes that G2. So that is also inside of the image. So that basically says that the image is a subgroup of G prime. So I have a mapping between this group to this group. So therefore, phi is a group homomorphism. Okay, and we have demonstrated this property in there. So phi is a group homomorphism. Now, let's demonstrate that the inverse business. let's demonstrate the one-to-one property first, okay? One-to-one property first. So, supposing that there's this thing, that there's this coset, and there's another coset, and suppose phi of G1 is equal to phi of G2 or phi x in this way in here. Okay. And so what that means is that since this is equal to FG1 by definition, this is equal to FG2 by definition. Okay. So that means FG1 is equal to FG2. It means FG1 is equal to FG2. And so this means FG1 times if you multiply by FG2 minus on the right-hand side, let's say, okay? And so F1 times FG2 inverse must be equal to what? E, right? Must be E prime. It's the thing, is that okay? If you multiply by FG2 minus. But this is equal to F of G2 minus, because this is a group homomorphism, okay? So therefore, this implies that F of G1 times F of G2 inverse is equal to E prime, but because this is a group homomorphism, this is equal to G1, G2 inverse, that must be equal to E prime, okay? For group homomorphism, what must this be then? The group homomorphism. There's only one element that gets mapped to the identity, and that is the original identity. Okay? So that means G1, G2 inverse is the identity. So that means what? G1 is equal to G2. That's a one-to-one property. Okay? So, in other words, if, wait, there's one more step. One more step. One more step. What this means is that G1, G2 inverse is in the kernel. Not the, I'm sorry. Wipe out what I said, okay? There are more things that gets mapped to the identity, okay? Because there's a kernel. The kernel is not just a single element set. So what that means is just that this thing is in the is in the kernel, okay? Because this thing gets mapped to the identity. So this guy is in the kernel. If this guy is in the kernel, then it means that by the definition of the cosets, that the coset specified by G1 must be the same as the coset specified by G2, okay? And so now I have proven the one-to-one relationship, okay? What this means is that if you have two sets in here, okay? In other words, if you get two things, G1 and G2, that gets mapped to the same thing, okay? Got two things, G1 and G2, that gets mapped to the same thing. Let's say this is G1, this is G2. What we have shown is that if you have two, now you don't know in the beginning whether these are equal or not, but if you just write it like this, two different things get mapped to the same thing, then these two different things must be just one and the same thing. So that proves one-to-one, okay? So that proves one-to-one, and then finally we have to prove also the surjectivity, and that is to prove that the map phi is also onto. Now you take any to prove onto. you take any G prime in the image of the map F. That means if G prime is in fact in the image, that there must be a G, little g and big G, such that F of G is equal to G prime. Okay? But by the definition, this gives F of G is phi of bracket of G by the definition of the map phi. Okay? So that proves surjectivity because that proves the onto business, because for anything inside the image, there is always something in the original quotient set which gets mapped to that thing in the image. So it's an onto map. So it's a one-to-one and onto maps, and so therefore it's an isomorphism. I think this then completes the proof of the so-called group homomorphism theorem. And the group homomorphism theorem is a very basic theorem in group theory, which will find many applications, I guess, both in math and in some physics problems also later on, okay? Especially when we talk about, we're going to apply these things to the rotation group, because in physics, our main interest, our main interests is in the special orthogonal groups, or just the orthogonal groups. Later on, even in the SU groups, and so the unitary groups, and so on and so forth. So let me point out one such application of this, as I just said, and actually these are exercises, but let me mention the results, and hopefully you'll see that it makes sense. So one special example of the group homomorphism is this, okay? So let's let the group, so in the abstract, we started off with these groups, okay, G, G prime, and K, right? K is the kernel of G, and so on and so forth. Let's take G to be O3. That's the orthogonal group, 3 by 3 orthogonal matrices, okay? Let's take K to be SO3. SO3 is obviously a subgroup of O3. It is the set of those 3 by 3 orthogonal matrices whose determinant is equal to +1. There are some others in O3 whose determinant is equal to -1, okay? Those some other things, so the group O3 is partitioned into two parts, one of which is SO3. Now, does the other part, which is a subgroup, SO3 is obviously a group in itself, so it's a subgroup. Is the other part a group? No, why? It doesn't contain the identity, because the E necessarily sits in SO3. Okay. The exercise asks you to prove that SO3 is also a normal subgroup of O3. SO3 is also a normal subgroup. That's not too hard to prove, okay? So you're asked to prove that. SO3 being a normal subgroup of O3, we can then form the quotient group of O3 divided by SO3. So we'll look at this thing in here, right? O3 divided by SO3. Quotient group. So like this is O3. This is O3. Inside of which there's SO3, which is a normal subgroup. Okay. And it so turns out that these are the only two cosets, so to speak. Okay. One of which is this one, which is a normal subgroup, which can be considered as the identity of the quotient group, and the other thing is the other group element in the quotient group. Okay. So therefore, by the group homomorphism theorem, there's this thing is just two elements in it, the quotient group. So there is a group homomorphism which maps the quotient group to a group of two elements in it because they have to be isomorphic, okay? And what do you guess that other group? That other group has only, it has only two elements in it, okay? Usually, this gets mapped to by phi. The quotient group gets mapped by phi to this group, which we can write the two group elements. I'm not going to use E now. I'm just going to use 1 and minus 1. Obviously, the 1 is an E. It's an identity because the multiplication rule for these two elements is just the ordinary multiplication rule between the two numbers 1 and minus 1. Okay? That being the case, the number 1 is obviously the identity in this group. There are two elements in here, so there's a very simple multiplication rule. 1 times 1 is 1. 1 times minus 1 is minus 1. 1 times minus 1 is minus 1. And minus 1 times minus 1 is 1. Okay? So that's a group. That's a group of two elements. It's called dihedral group. I mentioned that last time. Only two elements. And you take any element, multiply that by itself, you get back the identity. Okay? 1 times 1 is the identity 1, and minus 1 times minus 1 is also the identity 1. Okay? Okay, and now, what is the original group homomorphism, F in this case? So, our construction says that you begin with a homomorphism which maps O3 to this dihedral group Z2. Oh, actually, let me rephrase this. Let me not use this first. Let me use the F in here first. Okay, from the original group O3 to this dihedral group, which I'm going to call Z2. 2 stands for that there are two elements, one of which is the identity. The other element is whatever it is. Yeah.
Are we mapping a quotient group?
Not yet. Let me consider the original group homomorphism first. Okay. In this theorem, there's the original group homomorphism, and then you form out of this group you find a normal subgroup, and then you make a quotient group out of this group, and then there's an isomorphism now between this quotient group and the image group. Okay, the image group. Okay, and you see that the image group is also this guy in here. Now, so let me consider this by a very simple mapping. You define for some G in O3, you define f of G to be the determinant of G. Okay? Determinant of anything in O3 is either plus 1 or minus 1. Okay? And so it is those two things which constitute the dihedral group Z2. Okay? So this is obviously you can show that this is a homomorphism also. Okay? And now, what is the image? What is the kernel of this mapping? SO3, because it's precisely those elements in SO3 that gets mapped by this mapping to plus 1, which is the identity in the group Z2. Okay, so the kernel is SO3, and so that you can, and as I said, you can show that this is a normal subgroup. Also, SO3 is a normal subgroup of O3. Therefore, you can make a quotient group, O3 divided by SO3. And so you can write the kernel of the map of the group homomorphism F in this case is just the normal subgroup SO3. And now I don't think I have time to, but let me just quote the result to you, okay? And so, as I said, O3, the group homomorphism theorem says that the quotient group O3 divided by SO3 gets mapped to a set of two things. The first one is SO3, and then the other thing is, I'll explain what this means. This means a fixed group element in O3 multiplied by everything in SO3. This S is defined to be the inversion. In 3 dimensions, it is precisely this. This is an O3, okay, because this is obviously orthogonal, okay? The inverse is equal to the transpose. The thing is that the determinant is -1. So this is not in SO3, okay? So, yeah. So this, obviously, then this homomorphism, because this is a set of two things, one of which is this one, and the other one is this one, which is everything else in here. Okay, two things. And so, and meanwhile, this picture is actually just that. Okay, and so you can show that that this is the homomorphism. So which I think I'll complete. Actually, because of this relationship. And you can show that this corresponds to +1 and this corresponds to -1. So this is effectively the group Z2 also. Okay. So in this case, there's this group structure to the quotient group. Obviously, it's a group. The quotient group is a group. Okay. In this case, it's particularly simple because the quotient group is just the very simple dihedral group. Okay. I think we should stop here today. Okay.